So when we are looking at containers, let's recap, we have containers versus virtual machines. And we will, at this time, not much focus anymore on serverless computing. We will be just focusing on virtual machines versus containers, because this is the most mature technology at this time. Containers are an abstraction that we have already introduced, is a layer over the runtime environment. Multiple containers can run on the same kernel without any issue. However, we need to be worrying about security. Containers take up less space than virtual machines, and we are talking about megabit size rather than gigabits and so forth. And so it's a really good advantage of using virtual machines, using containers. Virtual machines, on the other hand, are an abstraction for the physical hardware. As part of the operating system, we have a hypervisor that allows multiple virtual machines to run on a single machine. Each virtual machine includes a full copy of the operating system. Now let's go a little bit back in the history and see how do we actually create containers, and what is actually a container technically. We have now heard about our understanding about this in a more abstract fashion. Let's take a look at the history. In 1979, we, for example, have change-root, which is a part of the Unix operating system, which allows us to change the root file system of the operating system to a new local location, so that the owner has isolated access to this. We make a big jump to the year 2000, where jails were improved. Naturally, a lot of other things happened in between, but let's just focus on what has happened recently. This adds a process sandboxing feature for isolation of the file system, the users, and the network. In 2001, the vServers were introduced, which introduces a concept of isolation called virtualized private server, and that's commonly used in web hosting services. Naturally, at that time, everybody talked about web hosting and bringing up web servers and so forth, and so this was a natural evolution at that time. Solaris containers and OpenVZ were introduced in 2004 and 2005, where isolated file systems were introduced, users and users groups, as well as a process tree, network devices, and IPC objects to do virtualization. And then in 2006, a group at Google defined something that's called process containers. And process containers limited access to accounting or introduced access to accounting, isolation of resources such as CPU, memory, disk, and I/O. This project was continued and renamed in some form to control groups in order to avoid name conflict to the term containers that at that time was used for many other things. This work really led to a revolution in our current understanding on how do we develop systems, and control groups are essential to the implementation of what we do today in Docker, Kubernetes, and LXC. After control groups were introduced, LXC used them, including the namespaces, and developed lots of APIs for different languages to use these isolation features to implement containers. Additional work was being done, for example, by Google that we will not go into much detail, but Docker came soon about at 2013, and we will be talking about this in much more detail. Also, Apache Mesos is important to name, and Yarn. I'm not entirely sure when these projects have been defined, so if you know the exact dates, just let me know and I can correct it in this image. I just used the 2013 because that was the first Apache Mesos paper I could find. CoreOS is actually a company that introduced some very important services, such as, for example, the runtime for containers or container engine called Rocket, and which allows you to start securely services or containers. etcd, which is key value store, Flannel, which is a network. Together, these services allowed us to create containerized environments. This has been also enhanced by for example, Kubernetes, which refines essentially the functionality of Swarm, Docker Swarm, which is allowing you to use containers across multiple machines. And there was a long debate between using Docker Swarm versus uses Kubernetes. And these days, a lot of people have actually adopted Kubernetes, which is in many aspects less refined, but allows more configuration aspects. So it's essentially more portable to other systems. And we will see most likely that both systems will be continue to be used, but Kubernetes has reached dominance. Another important achievement was that in 2016, Microsoft actually supported Windows containers straight into their native operating system. This now brings it into a completely new world, because not only are we talking about Linux, but we are talking about also Windows. So containers become really a cross-platform tool for anybody. So once I've actually developed a container on Linux, I can use that same container and start it on Windows, under the assumption that I don't use any underlying operating system features that are unique to these systems. So we already pointed out previously that containers have a performance advantage. And when we are looking at the literature, we find, for example, good examples where someone compared, for example, a Linpack performance benchmark, what happens when I execute it natively on Docker or on a virtual machine. And as we can actually see here is that the Docker performance is very, very close to the native performance, while if I'm using a virtual machine, in this case KVM, it actually suffers significant performance penalties. If I do, for example, a random read out of the Redis database, I can see the same thing. So in green we see a really good performance that almost is on top of the native performance, and the performance in the KVM versus the number of reads is actually falling down quite rapidly. When we do this with MySQL as a benchmark, we see the same behavior. KVM is really slow. Native performance is fastest. Docker, based on net host volumes, and then NAT volumes, and then NAT OFS services, is relatively close, and or actually the virtual machines can simply not compete with this. That's naturally appealing, because I can utilize my software in the most effective manner. Let's take a look at the building blocks that are needed in order to build a container system. Containers and containerization implements a virtualization at the operating system level. We pointed that out. With a kernel support allowing to share hardware and operating systems between multiple containers. Remember this is what we've said to you earlier. This is really an important piece. Containers provide a mechanism for aggregating, partitioning the set of tasks and all their future children into a hierarchical group with specialized behavior. We achieved this while leveraging the Linux kernel modules, C groups, and namespaces that enable separation between containers. I encourage you to look these two technologies up and find out a little bit more about it, so that you can understand how elementary these two technologies are. No hypervisor is used in the container, as we are using lightweight virtualization, and thus we are in a different level than, for example, KVM. Important tools that actually have enabled containers was LXD, LXC, Docker, CoreOS such as Rocket to provide container management features. So we'll go into each one of these a little bit more in detail. These days we mostly talk about Docker and Kubernetes. To enable clusters of containers to be scheduled in a group of machines or resources, we need to have a container management system. For this, we, for example, see Kubernetes, Mesos, and Docker Swarm. So let's revisit what actually a C group is. And a C group allows us to look at the machine in the following form. We need to be making sure we support resource management of resources within the machine. This includes CPU, memory, network traffic, disk I/O, and other subsystems. In order for us to achieve fine-grained allocation of this, we need to be having some kind of mechanism to allow us to define quotas, to define time periods where we can access this thing, and we define how we can share this with, for example, other users. In order to achieve this, we have essentially a description that allows us to do that. And when we are looking at a machine that, for example, has n CPUs and m memory in it, we can, for example, say, I would like to have from this n CPUs X amount of CPUs and Y amount of memory. This is then associated with the instance, and the C groups are responsible for making sure that that particular allocation takes place. The rest of the resources are being remaining in an allocatable pool. So this means that I can actually use the groups which are organized in some directory structure to manage my resources on the computer, and that is being utilized by the containers, allowing the container to isolate essentially access to the resources on that particular machine. So one example is, for example, how can Docker, for example, figure out what do I need, how much memory I need, and Docker has actually added wonderful flags to its interface to specify such resources, such as, for example, memory. Similar tools you may actually know from Linux. So if you remember the nice command or the limits file of configuration, so you can view it somewhat similar to that, but it's a much more defined way of doing this. So now this is really super useful because I can now utilize this for microservices running on containers even, where I can even have further breakdowns of the resources. So if I have a resource offered in my container, I can even further split this up into microservices if I wanted to do that. Namespaces are super important because we can here isolate really the names and essentially the process regarding of in regards to system resources. This includes the mount points, which is MNT, the process ID, the network, the inter-process communication, host name and uname activities in a Unix time-shared system, the user ID, and then naturally the C groups. So these namespaces are important because I can isolate certain things from each other because I have these namespaces that separate processes, and in this way I can implement containers that are having in different mounts, different process IDs, different networks, and so forth. A container instance system such as Docker sees these virtualized resources as an abstraction of a host system. So for each one of these systems, I actually create my own namespace, and I can operate in them, and it just looks like a normal Unix system for them. In addition to this, I need to be having a security isolation. For that, we utilize Seccom, AppArmor, and SE Linux. These containers have options to provide enhanced protections while reusing these components. There are enhancements to Linux and kernel enhancements, such as secure comp, and they restrict, for example, the system calls in such a way that the host system wouldn't be compromised through, for example, the activities that you're doing. So you can restrict read, write, or exit and SIG-term commands in order to make sure that they can't do any harm to your system. And so Unix has gradually been enhanced with kernels that provide these activities and functions for them, so that they can be reused as part of the reimplementation within, for example, Docker containers. One thing, for example, that you find is that the reboot syscall is blocked by Docker to make sure that we can't exploit the underlying system. So because we have these kernel enhancements that we now can actually allow or block through, for example, containerized applications, the applications become less powerful, and they can be executed in isolation on the system while giving them some limited amount of control to the system. AppArmor and SE Linux restrict process actions and control audits. So secure computing restricts the system calls, so we can run containers with limited system control. AppArmor and SE Linux restricts the process actions and the control audit, which with a rich profile, so that we can see what they are actually doing in the system, while at the same time restricting access to functions that could be potentially be harmful. The first system developed was actually by Canonical through is LXC implementation, which is really the important origination for the current container developments in general in all current efforts. LXC is a short for Linux containers. It's really one of many virtualization systems for Linux, but that has really made it possible to run containers. It provides a user space programming interface to Linux containment features that we just explained to you before. And so instead of you having to redesign and rework all this stuff to manage a container, they've written a wonderful library that you can use in order to make that container management possible. On top of LXC, they have developed an add-on library that provides now the management system for LXC using the API. And this is being done through a REST API for LXC. And now you actually understand why we are so emphasizing you to understand the REST philosophy and the REST programming, because this is an underlying base technology that you will be having in all different systems. So LXD also provides an add-on feature to do, for example, live migration. So this was originated in Canonical, which means Ubuntu in this case. And this also explains why a lot of people at the beginning, a couple of years back, didn't actually use other operating systems. They all wanted to use Ubuntu because of these particular features being offered within the operating system. Today this has been leveraged because Docker and others have replaced LXC with their own implementations, and no longer dependence on LXC is needed. Moreover, Docker also provides such mechanism now on Windows, so that even Windows is being supported. So we are not just having one operating system supported, but we have a whole array of operating systems supported. In addition to this, this is important to note that we need to have sometimes file systems that we want to share. And one of the systems that we want to do is can I share data from one container to the other? And there are different file systems available that you may want to look into and explore. This is one of the wonderful technology group exercises that you could do to investigate a little bit into these file systems, where they have been used, if they're still used, what they're being used for, and what that technology actually is about. We see Fuse is a very popular file system interface that is actually hosted in the user space. GroupFS, which is an option to give the container a native C groups file system so that you can access and manage C groups. OverlayFS is a unification of an integrated multiple file system that you can mount the file system in a unified form, so you have multiple file systems that you can mount, and you don't actually care what file system it is. This just looks like a one file system. So this is usually a read-write directory tree to be overlaid on top of another one. So this is typically kept very simple. And then the LXCFS is also user file system based on Fuse. So take a look at these, or let us know what they can and cannot do. That would be a wonderful addition to the class. Now we have introduced you now to the concept of containers, and we have given you two motivations. One for why this motivation is happening on a technical, historical reason, but also the other one why companies are so keen on pushing this technology and investing a lot of money in pushing this technology further. We also believe that the IT will be adopting this technology rapidly, even faster than we currently see. Now let's take a look how we actually move towards Docker. As we pointed out previously, we have introduced you to LXC, and LXC is a technology developed by Canonical. And if we compare the Unix trends, LXC versus Docker, we see an astonishing trend that after Docker was being introduced, we are seeing now a heightened interest into this. And it runs now on everything, including Windows PCs. The next thing that we need to be looking into is what's the difference between LXC and Docker. Initially, LXC was just a library that was providing us access to Linux containers. It was based on namespaces, C groups, SE Linux, and AppArmor, and sits on top of the Linux kernel. So all of this stuff is part of the Linux kernel. LXC uses this, enables us to do containers. So Docker, however, has changed this because this was originally one big library and split it up in multiple components that includes a Docker engine that actually allows us to run containers on the machine and schedule them. Containerd, which manages essentially the daemon to organize all of this. A containerized shim that is associated with the container as well as the runtime environment, so that we can separate the whole architecture in a number of smaller components. This allows us to port each one of these components onto a different system in a more straightforward fashion and in a more simpler fashion. Thus, porting to other operating systems and other environments is becoming much easier and has been successfully applied. So as we now see, Docker runs on Windows. That's actually really a good achievement. So when we are looking at this is really important to also understand what actually is a microservices architecture, which means a cloud-native architecture. And this has sprung up over the last few years to describe a particular way of designing software applications as suites of independently deployable services. Remember, our containers are next to each other. They are kind of services. They are all independent running, but they have a lot of stuff in this. So this is not just driven out of the air, but microservices introduce yet another concept on top of containers, where we are not just talking about the container itself, but we are running a service in the container that is still being a smaller unit. So while there is no precise definition of what this architectural style actually is, certain common characteristics are identifiable. This includes, for example, things that are centered around business capability, automated deployment, intelligence and endpoints, and decentralized and control of the languages of the data. So what we see is we find the following properties: a set of narrowly focused services, a set of independently deployable services, a set of services that can fail. And this is really the reason why I put up the slide, because anything that we can do here in the cloud has the problem of it can fail. No matter what we do, things will fail. And we have to design the containers, we have to design services, functions, under the assumption that things can fail. This has a really big implication for anything that we are doing. The advantages include really the increased agility of this individual service, because we can isolate it and we can deploy it on different platforms. We can increase the resilience of these containers while focusing on a small function. And containers allow the implementation of microservices. This is how I understand we will be utilizing containers within the class. Instead of running tens of services in a virtual machine, we will run hundreds or thousands of services in a containerized environment on the same machine. And this in such a form that we assume that we are focusing on very focused services, that the services can be independently deployed, the services can fail, and we will be using containers to enable the deployment of such services. It's important to understand why this is so different from past years. Docker has designed its container solution around microservices as a philosophy and recommends that each container deal with a single concern. So this means that we are not developing a container, for example, to host a database A and then do another function B and then do a third thing C. They just simply say, host this here in this container, and then your container talk to each other. So there is a single concern with the container, so we can combine containers and bring them together and put the application in a nice networked environment. This contrasts large enterprise data center applications typically that in the past have written one gigantic 3-tier application. What we here, however, do is we have integrated our application in terms of management components, and we create a loosely coupled application while picking the features that we really need. We don't need everything on another system. If you want to run a chemistry application, I don't think that we want to install an astronomy application on your computer. We need to be just focusing on the chemistry application. Therefore, we can limit what is actually happening on these containers and need to have on the containers, because we are focusing so clearly on the application that we are trying to do. Docker is the new way of doing this. LXC has previously provided this microservices architecture, but since everybody is now moving to Docker, we will be sticking to Docker also. This reminds us about the words spaghetti code. So you may have heard about this. This is no one can understand any code anymore because everything is now dependent on each other. This was a term in the 80s or in the 90s where people wrote lots of components that depended on each other, and we used workflow systems to combine these. And here's a graph that showcases this. In the 2000s, we have introduced into the spaghetti code layered architectures, and a lot of people really made sure that we have layered architectures. And now we see the microservices area. So where we see here is we are no longer interested in just layers or just the workflow, but we are creating certain things that we really like to eat, and we put together the necessary infrastructure that we really want, and this is being represented by the last picture. Another important term that is being used also in this area is the cloud native applications. This is how can we enable ourselves to utilize all of this and make sure that our applications in the cloud are running and actually working. And for this, we have to look a little bit more deeper into how these systems are being designed. And we need to be reminding ourselves that we are building applications from the ground up, from small stateless microservices and containers as functions. This supports a really different way of scalable parallelism across all the applications and services that we are trying to install. It also allows us to conduct rapid application modification and evolution, because we are only concerned about the modification of some small option. However, we still need to be making sure that that modification is being valid within the entire enterprise and within the entire application that is being deployed in the cloud. So in order to do this, we are now have multiple technologies work in conjunction. One of which is the DevOps technology, which we will be describing you in another lecture. It essentially says is instead of just giving the system administrator the right to install something, the developer has the right to install something through, for example, microservices and containers, and we take the system administrator a little bit out of the equation. However, when we make changes, we need to be making sure that we deliver them in a continuous fashion to the cloud services that we have already deployed. So we need to not only test the services, but we also need to be delivering these services, and we don't want to disrupt the delivery of an ongoing system. So it needs to be always up and running. Containers and microservices are helping to essentially provide these cloud-native applications. As examples from companies that have adopted this particular process, that has an always running infrastructure, that uses DevOps to improve their infrastructure, that uses microservices and containers in the back end, we see Netflix, Facebook, Twitter, Google, Azure does do this with billions of transactions per week in the Cosmos DB. The Invent Hub has trillions of requests per week. Cortana, IoT hubs, Skype, Power BI, CRM Dynamics, Kinesis, and serverless. So as you can see, this has been adopted and is the industry standard. So it's not sufficient to just use Python or know Hadoop or know all of these languages that may come towards you, but you also need to be understanding how these systems are all functioning together. So I have already pointed out to you that DevOps is an important part of this. We need continuous delivery. Things need to be done quickly and reliably, and also at runtime when things are still running. We have identified microservices are an architectural approach to building these systems, and we have a lot of APIs that we can utilize in order to make them handling. And container is one of the major basic components in order to make this happen. benefits to this is clear when we are looking at the enterprise. We can develop self-managing infrastructures through automation. That means cloud-native practices go beyond ad hoc automation that are built on top of virtualization platforms. Instead of we are just focusing on orchestration. The reliable infrastructure and application is achieved because we use cloud-native practices to ensure that much easier applications and services are being developed, which are easier to verify, and failures are better to be discussed or identified. We obtain deeper insight into complex applications because we are looking at, for example, the ability to create sophisticated health monitoring tools, which are looking at different services to be integrated into the same infrastructure. Security is enhanced because we can isolate certain things, and it's identified to be integrated from the start on rather than as an afterthought. And we have much more efficient use of the resources. So the software has been grown significantly, and microservices allow us to break down a complex system in very small, manageable tasks that are being developed by a multitude of groups and people. And nowadays, software teams are distributed to develop these microservices, and which enables really the team to work on each one of these small pieces in isolation, and are introduced through communication layer back into an overall system. So software development has been, or is being at this moment, completely transformed from being just focused on a programming language, a function, or an object-oriented programming framework into a microservices architecture. So let's get back to Docker. We have given you now what Docker will give, because we can implement microservices. And we have already pointed out to you previously and a while back that it's based on containerd and run C. It runs on hosts. We can have clients that can connect to the daemon to it, and which is its primary interface. We have images. These are capabilities and terms that we are using. We have containers. These are runnable instances of Docker images. We have a registry, which is a private or public registry of Docker images, in which we store the images. And we have services, which are essentially a service of containers. In this particular case, we have a service system that's called Swarm for Docker, and which was introduced in one earlier version of Docker. Previously, it wasn't distributed with it. When we look back at the key differences between LXC and Docker, we have to remind ourselves that there was certain reasons why Docker became so popular. We pointed out that systems have been compartmentalized, but we can also see that what are the differences between the two systems. So when we look at LXC, we find the file system is file system neutral. Containers are like virtual machines. That's how LXC started. So they didn't. The focus wasn't really running on thousands of containers on the same virtual machine, on the same resource. Data can be saved in a container or outside, and then we can build loosely coupled composite stacks that are part of the container. In Docker, we have the containers are made out of read-only layers through, for example, a particular file system, and that is supported by the Wise mapper. We have containers that are designed to support a single application. So while in LXC the goal originally was to still merge things into a more bigger container, in Docker we are now talking about single applications. And we need to be making sure that the data is persistently stored in volumes that can be accessed by the containers.